Can you see the slide? PDCCH.
Yes, sir.
Okay. Now, few things I'm telling you now, and it may be a little hard for you to grasp, but I'm sort of touching upon them. Okay. I hope to discuss them also later, but in different topics, under different topics. Okay. See, we already mentioned that when you first power up your phone, the first step is that it scans the whole bands and bands supported by the use, and then uh, finds out where it has energy. Okay, and there can be transmissions from multiple operators, definitely. Okay, uh, say Grameen, Robi, Banglalink, they all would be using the same bands. Okay, bands leased by the government. So initially the phone doesn't know the you may be a subscriber of Grameen, but the phone initially checks all transmissions from all the operators. Okay, in a later step it can find out the the right I mean uh, transmission from its uh, respective operator. Now initially it checks transmissions, and then it also performs downlink synchronization. Okay, otherwise it cannot read anything from there. Okay, so this is done for all different cells. Um, and uh, After this synchronization, it knows where the radio frames start. Thereafter, the first step is to read PCFICH, which tells how wide the control region is. The control region extends over the whole frequency bandwidth. Okay, so along the frequency axis, which is vertical for us, okay, we'll be using the time frequency grid this way: time horizontally and frequencies vertically. So vertically, the control region ranges um, the whole extent. It covers all the frequencies, and horizontally, it will be in the beginning of FC subframe, and it may take one, two, or three symbols. So PC FIC just tells you how wide it is. That's it. There is no other information in PCFICH. Then you are ready to read control region. After reading PCFICH, you can then in this control region there are different messages for messages of PDCCH, and there is also PHICH. Okay, PHICH we will mention later. Uh, PDCCH is actually the most important control um, channel in the physical layer. Okay, most important control layer channel in the physical layer. A number of PDCCH messages will be included in the control region, and their purpose is, basically you have these purposes for PDCCH. Well, the first is downlink scheduling. It means that there may be, say, 30 users who are, or maybe we say there are 10 users who are allocated resources in the downlink in the current subframe. Okay, okay, please try to visualize that. You have subframes this way. This shows you a whole subframe. You have two slots in there. Uh, each slot carries seven symbols. Okay, so you have one resource block, and this way in the frequency axis you have uh, many different resource blocks. If it is 20 megahertz wide, then you have 100. Uh, I mean, there actually it's actually pair of resource blocks because a resource block uses one slot in time. So it's a pair. So there will be 100 pairs of resource blocks if it is 20 megahertz. Now, in this subframe, different people will be allocated resource blocks for data transfer. We are still discussing the downlink, so it's about downlink data transfer. So many different people will be allocated, and they will be allocated different resource blocks. Basically, resource block is the granularity, the minimum granularity for resource allocation. So let's assume that we have 10 people who are allocated resources in the current subframe. Okay, 10 people. Now, uh, the PDC control region will have 10 different PDCCH messages within its control. Okay, and these messages will be, um, I mean, uh, dedicated for those 10 people. Okay, so one a message, I mean, the different messages are dedicated for those different people. One guy doesn't read the message for somebody else. And each of these messages will tell where the resources are allocated. I mean, which resource blocks are allocated to that particular user. This is downlink resource scheduling. Okay, so downlink resource scheduling. Um, okay, I could actually add the term resource here. I'll do that. Downlink resource scheduling. So that's I mean that's one of the purposes of PDCCH. Uh, Now it may be a question how you, I mean how you dedicate the PDCCH messages for different people. The PDCCH messages are actually called PDCCH instances. PDCCH instances, the term you see. So there are different. There can be many different PDCCH instances. The control region you see is pretty large. Okay? So there can be many different PDCCH instances. The reason the control region size has been made variable, okay, taking up 1, 2, or 3, is that it's unknown how many PDCCH instances you need. Okay, so if you need only a few, you can use up less control. I mean, less resources for control purpose. Okay, like you can make the control region narrower. Okay. Um, Now, okay, let's come back to this point. The every PDCCH has its CRC, the CRC of a PDCCH. Okay. CRC is probably remember that cyclic redundancy check is something used to use that allows uh, is something that allows the receiver to verify the correctness of the of that message. Okay. Now this every PDCCH instance will have its CRC scrambled by the identity of the UE. Okay. Each UE or will have some identities, and that identity is used to scramble the CRC. Okay. We'll talk about these identities later. It is these identities are mentioned here, but we'll talk about them later. Right now, I mean, I'm just giving you an idea how the different PDCC instances are separated. So every user checks the whole control region uh, and looks for PDCCH instances dedicated for himself. How does it do that? How it checks? It checks whether or not the CRC of the PDCCH is scrambled by its own identity. Okay. When it finds that okay, it is scrambled, okay, it considers it's for myself, and then only then it reads that PDCCH instance, which can include the resource allocation information. Okay. And that is like which resource blocks are allocated to that guy. So he will then go ahead and read those resource blocks and find out its downlink data. Okay. Uh, Now two things I'll mention here, but I think I mean this is getting too much at this point. Um, so I hope to repeat these points in future. Uh, these two things. The first of these two things are like I mean we have 100 pairs of resource blocks, but it depends how many users are allocated within that subframe. You may allocate these 100 pairs to only 2 people or 5 people. I mean, um, only a few people. I mean, a small number of people may be allocated, or you may allocate them to a large number of people, maybe 20 users. Okay, or even say 30 users or however. Okay, so each users will get a small number of resources. Now, when you allocate them to large number of users, then you need more PDCCH instances or PDCC. Okay, but when you allocate the resources to a small number of people, then you need fewer PDCCH instances. So the number of PDCCH instances required vary depending on how you manage the resources in the current subframe. Okay, so uh, you may allocate them. There is nothing specified. You may even allocate all the resources to just one guy, or you can allocate very small resources to every user, make the number of users very high. So this is why the control region requirement, size of the control region requirement is also variable. If you need a large number of PDCC instances, then you need a wide control region, okay, I mean spacious control region to accommodate all these PDCC instances or PDCC messages. On the other hand, when if you're allocating to just 2 people, then the PDCC instances will be fewer and you need very small uh, region. This is why this control region size has been made variable, because except the once you have the control region over, the rest you can use for real data. The control region is used only for control purposes, and so um, it is inefficient that you use wide control region. Okay, your data will be less in, I mean, data space is reduced. Okay, so this is the point why the control region size has been made variable. Just use as much as needed. Okay, and that requirement will vary from time to time. Secondly, the control region has been put in the beginning. Okay, it's because in the during the control region, when the phones are reading control region, okay, they are not receiving any data. Once the control region is over, according to the indication in the control region, they know, I mean, they will read data in different resource blocks. Now they know which resource blocks they have to read. Each user now knows which resource blocks are allocated to him, and he will read accordingly. He will read those particular resource blocks. So you have to put the control region in the beginning. You can't put it anywhere anywhere else. Okay, you have to put this information in the beginning of subframe, because based on this information, the UV will read, or the UV will use the rest of the subframe. Okay, so this is why the control region is put in the beginning. Okay, and this way every subframe will have a control region in the beginning with the information how you uh, deal with the rest of the subframe. Okay, and secondly, I'll seek your questions after I tell you uh, the uplink resource scheduling part. Well, first of all, you need to remember that this whole frequency axis, time frequency grid we are showing, is for considering FDD, is for for one side. Say this one is for downlink. For uplink, you have this whole set of resource block. I mean time frequency grid. A similar time frequency grid you have also in the uplink. But in the uplink, there is no control region. The control region you have only in the downlink, because the base station has to send you some control information continuously. Okay. In the uplink also there are some control uh, information transmission, but we'll talk about that too. But um, the control information loading is not that much. Okay. Here you have regular and pretty large amount of control information in the downlink. So in the uplink you don't have control region. Now in the for the uplink, the which resource blocks are allocated to you, I mean you can use for transmission, is also indicated by the E node B. So that is also indicated in the control region. There are also PDCCH instances to tell you which uplink resource blocks you can use. So for both downlink and uplink, resource scheduling is done using PDCCH instances. So if you have simultaneously both uh, data transfer, resource allocations for both downlink and uplink, so you will have two different PDCCH instances, okay, in the control region. You then find two different PDCC instances with the CRC scrambled by your ID. Okay. And when you read them, you find downlink data resource allocation information in one PDCC instance, in the other you find uplink. So in the uplink, it also tells you which resource blocks you can use. Okay. So, uh, the last two things, okay, except downlink and uplink resource scheduling, I'll discuss later. Okay, now questions. Um, Questions, yeah. Somebody, I think, wants to say something. Well, you're awake, right? After this boring explanation from my end, I think many of you have fallen asleep, and some of you may even be snoring, right? Some of you, yeah, many of you are apparently taking a nap, and some of you may be snoring now. Um, uh, yeah, I mean, if you are snoring, please raise your hands. If you're snoring, please raise your hands. See, nobody is raising hands because when somebody snores, he can't. He's in deep sleep. He can't raise his hand. Okay. So see, nobody is. Oh yeah, somebody has raised his hand. Okay, I see. Okay, then he must be uh, he must. I mean, he must snore like me. He snores while he's awake. Okay, good. And participation is also good, very good. Okay, we have almost all of you are here. Okay, no questions. If there are no questions, we'll go back. We'll go for discussion of synchronization, downlink synchronization. Okay. We'll later discuss downlink data transfer, and some of the things we have mentioned today will be repeated there. Okay, give me a second. Okay. Now, for downlink synchronization purpose, in LT also there are two separate uh, transmissions, but they are not called channels here. They are called some signals. Okay, synchronization signal, and those two, I mean, with similar to the CDMA case. Okay, here primary synchronization signal and secondary synchronization signal. Uh, in the case of CDMA, they were primary synchronization channel and primary synchronization channel, and secondary synchronization channel. Here they are called primary synchronization signal, secondary synchronization signal. Well, in fact, apart from the channels I have shown you, there are a few signals. Okay, uh, the we'll talk about some of the signals later. So these signals, okay, maybe I show you something. See, when we showed the time frequency grid, some of the resource elements are marked with different colors, and they are marked R0, R1, R3, R2. Okay. Well, these resource elements are not used for any useful data transfer. Okay. I mean, data is allocated to other resource elements in the resource block, but not there. So it looks like some wastage, but you need this uses. Well, in fact, for one particular transmissions, you have just one set, either R0 or R1 or R2 or R3. Okay. They are showing all together, but not all of them are occupied for the purpose I'm telling you now. Uh, Now, this this is some signal which we'll discuss later. Right now I'm just hinting you. Okay, so this signal is used for channel estimation purpose. If you have good estimation of your channel, you can set your receiver circuit, the equalizer, and everything, your whole receiver circuit better. Okay. So, uh, just for the channel estimation purpose, and we'll also show you that the position of these resource elements. Okay, I mean these are known signals. The EV knows which what has been transmitted, and this is resource elements. Okay, so depending on uh, depending on what it is receiving and what it should receive, it can set the receiver circuitry. Okay, so that you have proper uh, data recovery for all different resource elements. And we'll later show you that the spacing among these resource elements, okay, which are used just for channel estimation, depend on coherence bandwidth and coherence time. You have them set in the time, I mean scattered, you have them scattered in both time and frequency, but with some spacing depending on uh, typical coherence bandwidth and coherence time in the solar environment. Okay. So these are, but these are not categorized as any channels. Up to 3G, all transmissions are categorized as data or control channels. Okay. The term channel was used for all types of transmissions. But in the case of 4G, few things, some transmissions which are used for this type of activities, channel estimations or something, okay, in the physical layer, they are not called channels, rather they are called signals. So these synchronization signals for downlink synchronization, primary synchronization signals, secondary signals are also like them. Here also you used them in two different steps, PSS and SSS, okay, in two different steps, but you don't need a third step. In CDMA, you had a third step where you used C pitch, okay, but here you can complete everything in two steps. In the first step, you use PSS. In the second step, you use SSS. Now, they have particular positions in the time frequency grid, okay, some fixed positions where they are. Well, we have the idea of radio frames, and then I mean 10 millisecond long radio frames and uh, subframes, 10 subframes in there, each 1 millisecond long. In one radio frame, you have twice transmissions, two times transmissions of this set, the set of PSS and SSS. In each set, you have them like this, that see in this figure, you transmit PSS this way using 64 resource elements, okay, uh, on one, I mean in one symbol period, but in the frequency axis, it is spread, taking up 64 resource elements, okay. And right before that, you have secondary uh, synchronous signal, SSS, again taking up the same length in frequency and also in time, taking one symbol period. And this way you have transmissions of them here, okay, which is actually the in the first subframe and in the second slot of the first subframe, okay. In the second slot, you take, I'm talking about FDD now, so they are made available, I said twice, in the first and in the sixth subframe. So in the first time, oh sorry, in the first slot, not second slot, in the first slot of this subframe, first and sixth subframe, in the first frame. And you use the last two symbols of the slot. So you have 7 symbols in the normally. So you, oh, sorry. Yeah, I'm right. You use the last two symbols. So you have 7 symbols in one slot. So the last symbol, seventh symbol, will be used for PSS, and right before that, in the second sixth symbol, you have SSS. So they take 64 resource elements, but thereafter you have 5 more resource elements with nothing with no transmissions. They have GTX means um, you have dis. I mean, it comes from discontinuous transmissions, but it actually means that you don't transmit any energy. Okay, uh, so these are included in PSS transmissions, but actually you don't have any transmission, any energy transmissions there. Actually, you have transmissions in only 64. So you have 5 on two sides. So in total, oh sorry, not 64, 62. Okay, 62. So 5 on two sides. So it takes up 72. So in total, it takes 72 subcarriers. And 72 subcarriers actually take 6 resource blocks. If you remember, in frequency, every 12 subcarriers form 1 resource block. So there are 6 resource blocks. Well, now this is a location you have around the center of your whole frequency bandwidth. So you may have 20 megahertz. So in 20 megahertz, you have 100 resource blocks. Okay, you have 1200 subcarriers for transmission and 100 resource blocks. For PSS and SSS, you take the central 6 resource blocks. Okay, I mean, find the center of the whole bandwidth, and around that you take 72 subcarriers or 6 resource blocks, and then transmit this PSS and SSS. Whichever, whatever the bandwidth is, if it is 10, 5, okay, 3, whatever, it will always be the central 6 resource blocks. Well, now what is the minimum bandwidth? The minimum is 1.4 megahertz for transmissions. And if you check there, you have actually 72 subcarriers for transmission in 1.4. So the minimum transmission bandwidth for LTE is 72 subcarriers. And that is what you used for PSN and SSS. So for PSN SSS, the size is made equal to I mean, what you occupy in the frequency is made equal to the smallest bandwidth. Okay. So I mean, this is to make sure that it fits in all possible bandwidths. Okay. Although occupying the whole for the minimum case. Now remember that we have twofold purposes. We have to find out the alignment in time, which is here the boundaries of radio frames. Right? You have radio frames one after another. So you need to find out where the subframes is start, but that doesn't give you the whole information. You also need to know where the radio frames start. So that is the time alignment information. One purpose of synchronization. Secondly, you need there should be different identities of the cells in a neighborhood, and so that the UE can distinguish, okay, when uh, it is in its initial operation. Okay. You have just powered up, it should be able to uh, separate the transmission from different cells. So different cells in the neighborhood will have different identities, and it should be able to uh, just identify what the particular identity is from this particular transmission and from someone else. Okay. Now, the these identities in the case of LTT are called physical cell identifiers, PCIs. We discussed earlier that the possible number of variants, okay, should be good enough so that there is no repetition in a nearby cell. But it doesn't need to be too high. You may not make it unnecessarily high, because when it is made, I mean, you don't, uh, if you have 500 around, we say that number is around 500, which can make sure that you don't have any repetition in a cell from which there can be signal. Okay. uh, to make a cell which repeats the identifier needs to be far enough, and for that purpose the possible number of variants can be 500. 500 is good enough. Okay. But you may not make the number of variants unnecessarily high, because that makes the process of separation more complicated. Unnecessarily you increase the processing time, okay, to find out what the particular identity is for yourself. Now this number was 512 in the case of 3G, and the identifier was called PSC, primary scrambling code. Okay, different cells are identified with their PSCs, and 512 PSCs were there. In LT, it is PCI, and 504 PCIs are possible. These 504 PCIs are grouped um, in with 3 PCIs in one group. So you have 168 groups. These are called cell identity groups. Cell identity groups. Okay. Well, actually, I mean, the purpose of all these groupings or whatever, the key purpose is to enable those two things. Okay. I mean, you also need to identify. Uh, I mean, in a easy way. Now, this another point I'm telling you that um, these cell identity groups are have, I mean, in the case of LT, they use 3 PCIs in one group, and a beauty here is that usually a base station has 3 cells. This is the most common number. So what people do, a E node B, an E node B is allocated one cell identity group. One of the 168 possible groups are allocated to one E node B. And then in that E group, you have 3 different PCIs available. The 3 cells under the E node B will be allocated those 3. Usually, I mean, these are called alpha, I mean, the cells under one base station is called alpha, beta, gamma. I mean, it's not specific to LT. In all generations, the 3 different cells are called alpha, beta, gamma under one base station. So under one E node B, you have alpha cell, gamma cell, and alpha beta cell, and gamma cell, and they'll be allocated the 3 PCIs of one group. Then uh, we go back to our discussion on PSS and SSS. Well, the only process available, okay, to find out time alignment or to resolve the synchronization is correlation. Okay. The UE tries to find out where you have this PSS located. Okay. You see, if you can find out that PSS and SSS are located here, okay, then you you know that that is the end of a slot. Okay, so from there you can actually find out the beginning of a subframe. Right? So in the case of CDMA, we first resolve the slot boundaries. Here we can first find out the subframe boundaries. You uh, try to find out the location of PSS, and once you find out the location of PSS, you actually know it could be PSS of the sixth subframe or the first subframe, subframe number 0 or subframe number 5. You don't know initially. But if you know PSS, then you know that it's one of them, okay. But you can identify the subframe boundary. So what the phone does, um, it starts uh, doing correlation. Now this PSS, it's a PN sequence, but this PN sequence is generated in the frequency domain. Okay, in the case of CDMA, it was a time frequency generation of PN sequence. So in a whole time period, you complete the whole detection. Here, in the case of OFDMA, you also have different subcarriers. Okay, in 3G you had just one carrier in frequency, but here you have many different subcarriers. So it takes the advantage that it generates a PN sequence in the frequency domain. In frequencies, you generate different symbols, and you create a whole sequence. Okay, there are actually, you can play around with both magnitude and angle. Okay, for the symbols, and what they do, in fact, the type of PN code they use is called Jarabshu, ZC, and when they generate, they use the same magnitude, but they differ the angle. Okay. We won't go into the detail here, but the point is you have a PN sequence which is laid along the frequency and the frequencies. The advantage is that you need just one symbol to for the correlation and find out whether or not you have the PSS here. So Jaref-Shu PSS generation uses I mean, uh, can use three different routes with complete with orthogonal uh, sequence generation. Okay, it uses some route. I didn't write down the equation here for the JC sequence generation, but anyway, I could actually add in my book I used. Well, I will share the scan pages from my book, and you'll see there. So in the equation, there is a root u, and in place of u, when you use these numbers 25, 29, and 34, then the three different sequences generated have orthogonal relationship. Okay, so you have perfect correlation. So what do? You check with the particular ZF sequence in every symbol. After you power up, you keep checking. Maybe you have powered up here. So in this symbol, you keep checking. You go to, the frequency range of energy. Once you sweep through the frequencies, you know which part of the frequencies have the transmission. Go to the central part, take up the 72 subcarriers, okay, length. Okay, you know where you have what is the location in frequencies for PSS, and then on that PSS part, you keep correlating with your ZFC sequence with, for example, 25 root first. Okay, you do it on this symbol. If you fail, you don't have any correlation peak. On the same symbol, you try with the another root 29, and then try it 34. Okay, if it fails, move on to the next symbol. Now, in fact, all transmissions in all LTE networks use the same PS sequences, these three PS sequences. So it's the same with whatever operator you use. So you just use these three. That's it. Okay. Don't need to care which part of the world you are in or which operator you are working with. Okay. In all countries, with all operators, you have the same PSS sequences. Now you keep checking. So in every symbol you have to correlate. Okay, but that's not too burdensome because you have to correlate only with three different options. So you keep checking. Even when you have the yellow part, the yellow blocks are the SSS blocks. Okay, I mean here you should SSS and then PSS. Here it's shown in blue, but here in uh, here it's in yellow. So the yellow part is SSS. There also you fail. Then when you hit green, you will be successful with one of the three. Okay. Uh, so when I mean you get a correlation peak, first of all you have found which one among these guys is. Okay. If it is 29, so, then I mean let's assume let's tag them with alpha, beta, and gamma cells. So if it is successful, if you get the correlation peak with 29, it's a beta cell. If it is 34, it's a gamma cell. Okay. So you have found whether it is alpha, beta, or gamma. That part you have done. And also, you know that this is the end of your slot. Now you know what the symbol period lengths are. So you actually know where the subframe starts. So you know you have already resolved the subframe boundary. However, it could be the subframe boundary on this subframe, sixth subframe, or here, subframe 0. Okay. That you don't know yet. You don't know yet the radio frame boundary. You don't have to correlate too much because it is transmitted in every 5 milliseconds, if, right? So you have twice transmissions in every radio frame. So even if you hit, even if you start power up here, the process will not be too much. Okay, here you hit. So you have done this stage, and then you have got four types of information. Okay, what they are? First of all, you have now confirmed that you really have some LTE transmissions in there. Previously you got some energy, and you guessed that there might be really some LTE transmissions here in this band. I can see some energy. But once you do this step, you are sure. I mean, this way transmissions are there only for in LTE technology. So you are sure that it's there is some LTE transmissions, and at these frequency ranges, because the particular 72 subcarriers around the center will be used for PSS. So you have confirmed the center frequency, and that center frequency is called ARFCN. Like in 2G, we showed the carrier frequencies with numbers, and they were called ARFCN, absolute radio frequency carrier number. Probably that's the whole term. So here you add evolved for LT. Okay. So for every transmission, the center frequency is called EARFCN. Although you have a number of subcarriers, the center one is called EARFCN. So the center ones are all numbered. Okay. Again, you have different numbers. Okay. So you have then you have come to know the slot timing. Okay. Slot timing, and actually the radio frame timing is also known. You know where the slot ends. Now, cell identity within the cell identity group. You don't know yet which of the 168 groups have been used there. But in a group, there are three possibilities: alpha, beta, and gamma. You have already resolved which one among those three has been used there. Whether it is 25, which relates to, say, alpha, 29, which relates to beta, 34, which relates to. So you have, from your correlation peak, you know which one among the three. So you don't know the PCI. You don't know yet the PCI. But if you could know which one among the group is, you could tell the PCI. Okay. Uh, the search space for PCI has been reduced from 504. It had been reduced to 168. Okay. Like uh, in the case of CDMA, in the second stage, the search space was reduced from 512 to only 8. Okay, so here it has been in the first stage. You have two steps only. It has been reduced to, if you know this, the selected group is unknown, but if it were known, you could tell the PCI. So that's the third piece of information. The fourth one is that you can have is you can estimate the propagation channel, because PSS sequence you have detected, okay, with correlation peak. You know what uh, is the expected transmission there for PSS. The expected sequence is known, and that you have found. So the propagation channel always, somehow distort little bit, but your estimation, okay, you know what see, you know what you should receive. So from the difference, you can actually estimate the propagation channel. Okay, the estimation propagation channel can be used for recovery of other data. So that you can use this estimation in subsequent activities. The second stage, SSS. Okay, well, it generates two different codes. Okay, SSC1, SSC2, and the I mean for one group, 168, one of the 168 group uses two different codes. Okay, all with again on the frequency domain. Okay, it's 62 symbols long sequence. Okay, both PSS and SSS sequences are 62 symbols long. Then you have 168 pairs, S1 and S2. Now you put them in here. S1 is put on the first subframe, and S2 is put on the second. Subframe number 5 or 6 subframe. That's how you set them. And there are 168, but what it's made here that there is no other, uh, there is not another group which has uh, a pair of sequence, okay, that is the same S1 S and S2, or its reverse like S2 and S1. So the I mean, you could have S1 or some another sequence. Okay, one of the sequence you may use in another pair, another 160, another. I mean, you have 168 different groups. Okay. For I mean, each group corresponds to one set of group. I mean, a pair of sequences, and that sequence you used in the place of SSS. Now, the group, I mean, have unique sequence sets in the way that no two group have the same uh, group, the same sequences S1, S2, or its reverse. Okay. Another group doesn't have even S2, S1. You could have S1 and say another code. One of the sequence you can use in another group, and for the second sequence you can use a third sequence. I mean, for the second position you can use some other sequence. Okay, I'm not sure if I could make it clear. So now you again start correlating. Now this time there will be quite a few different variations. Okay, uh, it's not just three. Okay, it's not just three. You have many different variations possible. So you have to check with many of them until you get a correlation peak. You have to keep checking. So that increases the correlation process. But now you know the location. In the case of PSS, you had to you didn't know the location, so you had to keep checking uh, different symbols. You have to go through after power up. You have to go through all the different symbols until you hit. But after the detection of PSS, now you know the location of SSS. So maybe you have powered up here. Okay, so you have got first PSS here. Then you keep checking, and then you come back to the next subframe, next radio frame, and this is the first SSS location. After PSS, check the first SSS location, the first one. So that arrives almost 5 milliseconds later. So on that SSS, you try with different possible sequences until you get a correlation peak. It is not again burdensome, although you have quite a few different variations, because you know the locations. Only that particular symbol, you try the correlation. Okay, so once you hit, then you keep again. I mean, you have nothing to do in here. So you get to this symbol, and then again keep checking the other possibilities. Once you know, then you know what the other possibilities are. Check with all of them until you get the right one. Now, once you get the correlation peak here, you know which set you have here for the two positions. Okay, and then you actually know which one among the 168 cell entity group you are linked with. Okay, so it's your own of the or the cell entity group of the cell, one of the 168 groups, so that and previously if you the I mean one of the three possibilities of these, I mean, alpha beta gamma. So now you actually have resolved PCI completely. You know which one among the 5 and 4 PCI has been used in this particular cell. Secondly, you actually also find derive the radio frame boundary, because I said that the reverse of that sequences is also not present anywhere. There is, I mean, considering the reverse, there is a unique set. So since you know which one comes first and which one comes next, you know which one is the first. Okay. uh, for example, if you have powered up here, if you have powered up here, so you detect PSS first, and then you hit this SSS first. You have got something, then you hit this one. Okay, so now you know that this is the first one, so you know which one is the first, which one is the second. So you know, I mean, the location first and sixth subframe, so you know the radio frame boundaries. So you have the time alignment, and you expect the symbols to be located pretty much. Okay,